Today, I am going to discuss about spontaneity and stability in the perspective of thermodynamics, mostly metallurgical process thermodynamics, so that we can understand what is spontaneity and what is stability for any transformation or any product, any material with respect to thermodynamic understanding. Actually, spontaneous process, if you think about that, it is capable of proceeding in certain given conditions without you have to give anything outside source of energy or anything other than the process itself. It can go. So you can tell that a spontaneous process is basically capable of proceeding in given direction without needing to be driven by an outside source of energy. And the laws of thermodynamics actually govern the direction of a spontaneous process. We'll learn slowly in today's class. The laws of thermodynamics actually ensuring that if a sufficiently large number of individual interactions are involved, then the direction will always be in the direction of increased entropy. This is the one way to see the spontaneous process. In a particular spontaneous process, if you can think that slowly or in the direction of increasing entropy. If you take an example of endothermic process, then what it is that in an endothermic process, it's a chemical reaction where the standard change in free energy is positive and energy is absorbed. And in case of exothermic, just reverse the things. So the spontaneous process, what we understood that it is capable of proceeding in given direction without the requirement of any energy from the outside. So if you look at spontaneous process, it does not imply that reaction proceeds in a very high speed or great speed. Spontaneity does not imply that the reaction proceeds with great speed. This is very important statement. Spontaneity does not mean that the reaction or the transformation, the process will proceed very high speed. For example, the decay of diamonds of graphite, if you take, is a spontaneous process that occurs very slowly, very slowly, and taking millions of years. The rate of reaction is independent of its spontaneity. The concept of spontaneity is totally different with respect to concept of speed of reaction, the rate of reaction, the extent of reaction, how quick will be. That is, two things are totally different. One should not confused with each other. Every reactor in a spontaneous process has a physical tendency to form the corresponding product. This tendency actually related to the stability. Now you are understanding that spontaneity somehow have a relation or correlation to stability. Now we have to understand what is stability. Stability, what we understand that stability is minimum energy state. If you can reach through certain transformation to minimum energy state, if it is in the product direction, then the process will be spontaneous. So there is a very strong correlation between spontaneous process and the stability of product or reactant. Which one is more stable? That will decide the direction of spontaneous process. So now we are little bit have an idea that what is the concept of spontaneity. So if you go for combined form of first and second law for a closed system, then the equation will be du du is exact differential because u is a state function. Already we understood that. Equals to capital T multiplied by ds. Here ds is the incremental change in entropy and minus P is multiplied by dV. And dV is incremental change in volume. This is a fundamental equation which derived from the combination of first and second law for a closed system. And already we know what is closed system, where only energy transfer can be allowed, no mass transfer will be possible. The internal energy is a function of entropy and volume. And also we know that U, T, S, P, V are the state function. Now we have to understand this fundamental equation, how it's going to influence us to understand the concept of spontaneity. So for that, first we have to understand the internal energy concept, how it is related to the stability. The condition, if you derive, suppose one particle is moving in an external potential, suppose U, settles to a stable equilibrium at minimum value of U. So always you can understand that if particle is moving an external potential, that you can take as a U, and it will go to equilibrium when its internal energy U is minimum value. So this is a consequence of loss of energy from different way. It can be a frictional process, anything. So stable equilibrium occurs at minimum of the potential energy if you are looking at a particle moving from higher altitude to lower altitude, or higher height, so lower height, or something there. So in this way you can understand what is stability kind of concept. If you take one body and try to find out the position of residence of the body, which one is stable, the most stable is that thing when the center of gravity is much lower or closer to the Earth's surface. So the distance from Earth to the center of gravity will be less, and also center of gravity can be the middle of that overall shape of the body. So it is the concept of stable situation of a particular material or shape of size of specimen, how it stays in the surface. Now if you look at in the slide, that a change in process can occur spontaneously if the internal energy decreases when the change occurs at constant entropy and volume. So that actually we understood that if you want to get more stable scenario, you have to go such a way so that the internal energy will be decreased. And then only you can understand that how it will related to the spontaneity. And change in internal energy du actually, if you see, it is equal to dq plus the expansion work done due to the PV and the additional non-expansion work done. So if you take a system which is constant, which has constant volume, then that cannot do expansion work. So if the system also does not do any other kind of work, then what you understand that from the first law that du equal directly dq at constant volume. So in this way you can understand that there is a strong correlation with the heat capacity at constant volume with the internal energy. So that part also important if you want to understand how the internal energy are going to vary for a particular process. Now here you are saying that du equals to 0 when you are getting the equilibrium condition, and that means at equilibrium the things are not going to change. And when it's not going to change with respect to process, when the internal change in internal energy is equal to 0. So if you one that the process should be spontaneous, then always du less than 0 means always the internal energy are going to 0, going to decrease. And if the spontaneous process, then du greater than 0. This is the criteria for the spontaneity with respect to internal energy variation or incremental variation of the internal energy. So if you see at infinitesimal change in reversible process with constant S and V, du comma SV is less than equal to 0. This is the criteria of spontaneity as well as equilibrium. And if you check at constant entropy and pressure, the scenario will be that enthalpy dH change in incremental enthalpy, incremental change in the enthalpy at constant entropy and pressure must be less than equal to 0. When it is equal to 0, it is in the equilibrium. If it is less than 0, then it is a spontaneous. And if dH is greater than 0, then it is a non-spontaneous process. Because at constant pressure, the scenario is different. At constant volume, the scenario is different. Now we have to understand that Helmholtz energy and its application to understand the pressure effect of two phases with respect to equilibrium concept. So what is happening? Helmholtz energy and its application, if you want to see, the pressure of two phases must be equal at equilibrium. How to get that? If you see, if you check the Helmholtz free energy expression, A equal to U minus Ts. U is the internal energy, T is the temperature in absolute scale, and S is entropy. Now, if you differentiate this expression, you are going to get dA equal to du minus Tds S dt. Here, the U is also state function. Is you are can tell that is a thermodynamic potential. So now already you know that du equal to Tds minus Pdv. So in this way you are going to get dA equal to minus S dt minus Pdv. Now T and V are the natural variables. What is the definition of natural variable? Already we understood. If an infinitesimal change take place in a system of a constant T and V, then what will happen? dA TV less than equals to 0. So for irreversible process, A decreases. For reversible process, A must be constant. So this is the scenario. Now if you check a system, two phase of system in a container of a fixed volume surrounded by a heat reservoir. Suppose you are taking two-phase system in a particular container, and that will be a fixed volume surrounded by a heat reservoir. Suppose the volume of the phase alpha is increased by dV, capital dV, means incremental change in volume of the phase alpha, and the volume of phase beta same incremental decrease, but the value is magnitude are same, but there is a incremental decrease in the volume. So it's a decreased by dV. So the total volume must be constant. When equilibrium, the system we are going reach equilibrium, what will happen? dA must be 0. So what is dA? dA equal to minus S dt minus P dV. Now dA equal to, if you want to do 0, then that will be equal to dA alpha plus dA beta. Change due to this change in volume, the change in Helmholtz free energy of alpha and beta phase. So what you are going to get d alpha plus d beta equals to 0. Now you are putting d alpha equal to minus p alpha dv and p beta equal into dv equals to 0. So what will happen if you equate them? Then you are going to get that p alpha equal to p beta at equilibrium, because you are getting the condition of equilibrium when dA equals to 0 based on that. So now we understood that pressure of two phases must be equal at equilibrium if two phases are there. So in this way we understood that Helmholtz free energy actually help us to evaluate, to determine the equilibrium condition of two phases, if and the condition is their pressure should be equal. What will be the role of energy for the growth of energy. So you see the free energy actually talks about or from property compared for the application of the second law of the constant temperature and pressure. And why is it so? Because it can talks about the stability as well as the criteria of the that Gibbs free energy provides more convenient thermodynamic property compared to the entropy. And if you apply them in the second law at constant temperature and pressure. Suppose we are taking a case for isolated system. Why isolated system? Because we are taking a system which does not transfer across the boundary towards surrounding the mass as well as does not transfer the energy. So for a isolated system consisting surrounding at constant temperature and pressure, what is the change in entropy in the universe? Del S universe equal to del S system plus del S surrounding, and that must increase for spontaneous process. We know in case of spontaneous process, the entropy should increase. Overall entropy or sum of the entropy should be increased. And but if you check del of S surrounding equals to del H system by T at constant temperature. Now if you put same thing in the expression, what you will get del S of system minus del H system by T equal to del G by system, and that must increase. So you can tell that for a spontaneous process, change in Gibbs free energy of the system must decrease. So del H should be less than 0 or negative for a spontaneous process. The criteria of spontaneity of a process with respect to Gibbs free energy now we can identify. And what is that? Now del G of system must decreases, means change in Gibbs free energy for a spontaneous process must be negative. That's a very important understanding with respect to spontaneous process in the viewpoint of thermodynamics. Now if you see what is the two form of free energy, the Helmholtz free energy, it talks about A equal to U minus Ts, and which is convenient for constant volume. And if you talk about Gibbs free energy, then G equal to H minus Ts is convenient for constant pressure. Now if I take differential of A and G both, and can be written like that, d equals to du minus tds minus sdt, and dg will be dh minus tds minus sdt. For the temperature kept constant for the process, what will happen? dA equals to become du minus tds, and dg will be th minus tds. Now for at a constant temperature and volume, we already know that dA at constant T and V must be less than equal to 0. And same way, dG at constant temperature and pressure must be less than equals to 0. Thus, for a spontaneous process at constant temperature and pressure, the Gibbs free energy must decrease, and dG equals to 0 at equilibrium. These two criteria we are now understood with respect to spontaneous process. So in case of thermodynamics, a spontaneous process is the time evolution of a system in which it releases free energy and it moves to lower, more thermodynamically stable energy state. So till now, what we discussed, based on that, now our understanding, if we sum up it, so the understanding is like that. In a thermodynamic point of view, a spontaneous process is the time evolution of a system in which it releases free energy and it moves to a lower, more thermodynamically stable energy state, closer to thermodynamic equilibrium. This is the understanding what we got till now today class. Now we want to discuss that how does Gibbs free energy G behave overall as the state of a system changes. Now we have to understand that how does G behave overall as the state of a system changes. Why we should concentrate on the question? Because we understood that spontaneity of a reactions, spontaneity of a process, if it may be metallurgical or chemical, it depends on change in Gibbs free energy, and it should be negative for a spontaneous process. Now we have to understand how does that G behave overall as the state of a system changes. So for that, we should know that since the new criteria for spontaneous change is that G mass decreases. Already we discussed G mass decrease for spontaneous process. Now we can sketch the diagram given in the slide. We sketch diagram how it must behave as a system changes spontaneously. From the plot, we can see that the system naturally tends to roll down a Gibbs free energy hill until it reaches to the lowest point. So system always have a tendency to roll down a Gibbs free energy hill until it reaches the lowest point. What is the lowest point? That equilibrium state. The system is that then at equilibrium. Now we can see that a system tends to stay in a state of Gibbs free energy G of equilibrium because it must climb a Gibbs free energy hill to get out. Thus, the reason for change, the lowering of the Gibbs free energy can be viewed as driving force. Now we have to understand why lowering Gibbs free energy is the driving force or a tendency for such kind of changes. That if you see that lowering of Gibbs free energy can be viewed in the process as a driving force. Why is it so? Because in this plot, if you critically observe, you can understand that the system naturally tends to roll down a Gibbs energy hill until it reaches the lowest point. Lowest point means lowest Gibbs energy value, and the system is then at equilibrium. Now you can see that a system tends to stay in state of G of equilibrium because it must climb a Gibbs energy hill to get out. So it is better to stay there. This is the reason. This is the fundamental reason for change. The lowering of the Gibbs free energy can be viewed as a driving force or a tendency for a change. It can be applicable for metallurgical phase transformation. It can be applicable to certain chemical reactions. The steeper the hill, the greater the tendency for the system to change. Now we understood driving force is the Gibbs free energy. Lowering of the Gibbs free energy is the driving force. Now we understood. Now we have to understand that what is the relation between the steepness of that curve and the tendency of a change. And that statement is the steeper the hill, the greater the tendency for the system to change. So the Gibbs free energy driving force is relatively simple if you see in that it is made up to two recognizable factors, that is enthalpy and entropy. Again, I am repeating, Gibbs free energy driving force is, if you see, or it is a relatively simple thing, and it is made up of two recognizable factors, the enthalpy and entropy. It is useful in analyzing how each of these factors separately behaves when a change in occurs. The Gibbs free energy changes. So what is the Gibbs free energy relationship? Already we know G equals to H minus Ts. So it is basically made of two recognizable factors. One is enthalpy, another is entropy. Now we are going to understand how change in enthalpy and change in entropy plays a role with respect to overall variation in change in Gibbs free energy. So this is the point. So if you see in general, any process in which enthalpy decreases is favorable to decrease in Gibbs free energy. And if you see any process in which entropy goes up is also favorable to decrease in Gibbs free energy. This is a very general statement. It's not always correct, but generally it is happening. In other words, you can tell that system, like most people, seek a position of minimum energy or minimum energy and as well as maximum disorder. Means systems are really look for a scenario where it can have a situation where it is having minimum energy and maximum disorderness. This actually leads to minimum Gibbs energy and a state from which a system is reluctant to move. Already we discussed from the plot of that previous slide plot that this actually leads to minimum Gibbs energy and a particular state from which a system is not willing to move or not willing to deviate. Thus, the Gibbs energy, enthalpy, and entropy are three main properties we should pay attention with respect to understanding the change of a state. So, if you check, when a process is carried out in an open under constant atmospheric pressure, PV work is done by the system against the atmospheric pressure. And this work is wasted because this is not controlled. Thus, any useful work done by the system in the above case, what we have discussed few minutes ago, beyond this PV work is given by the change in Gibbs energy. Now we understand that from our overall discussion. So, for example, if you take certain example, in some electrochemical cell, gases are likely to evolve which expand against the atmosphere to do PV kind of expansion work, which is not used and is the only electrical energy generated by dWe. Electrical energy is equal to the dG, which is utilized if you talk about electrochemical cells. Thus, the maximum useful net work that can get from any constant temperature and pressure is del G, and del G is, you can say that is a non-PV work, and del H minus T del S. So, if you want to analyze the del G term in terms of del H and del S, because here you can we can already understood that key change in Gibbs energy is basically made up of two very distinct variables. One is enthalpy, another is entropy. So for that, we have to understand how del G are going to behave in terms of del H as well as del S. Suppose for a useful work done, del G and del H must be negative. If entropy term T del S is positive, then minus T del S will be negative. It makes del G more negative. So if you get a scenario where del H is negative and T del S term is very highly positive, then you are getting more del G negative. Thus, just del H and so increases the work done for us. So in case T del S equal to Q reversible, we know that is greater than 0. So heat is transformed from the surrounding to the system to help fuel the work. So in the reverse case where the system entropy decreases, suppose minus T del S now are become positive and del G is not as negative as del H. So the scenario heat must flow from the system to surroundings. So all of the del H is not available to do work. That concept is very important. Now all the available del H is not going to be available to do work. The heat flowing to surroundings increases the entropy of the surrounding sufficiently. So now that the process remains spontaneous. Thus, part of the energy of a system has to be sacrificed if you want to maintain the spontaneity. That is the very important part. And we can understand from the slide itself. If you check the slide, in this slide, there is a zero line and there is a positive line, one is a negative line. So in the first, you just, as per the value of del H must be negative. So what is happening? That del H negative part is there, and in first case what we discussed, till del S, T del S also be negative. Now del H and T del S both are negative, minus T del S should be negative. So for that T del S should be positive. So if we get such a scenario and then we add minus T del S, then we will get del G equal to del H minus T del S. This is the schematic representation of that part. But if the scenario is different, del H is negative but not so high in value. It's a smaller del H. It's not so high in the value that dt del S is now itself is negative. So minus T del S is positive. So it will cut out certain values from del H. So it will be the del G now become smaller, less negative. So if you see such a scenario, for del S equals to 0, the maximum network del G equal to just modulus of the del H. If del S equals to 0, means T del S term will be 0. So maximum what can be done? That network network that is equal to del G, and that equals to mod of del H. And del S less than 0, then it should be more than del H, the work done more than del H. Here you can see that. And if del S is greater than 0, then there is a chance that maximum network del G is more than mod value of del H. If you see that first case, and if del S is less than 0, then del S is less than 0, then the maximum network del G will be less than del H. And now if you say that how spontaneity depends on the temperature. If you see this table, sign del H is negative, del S is positive, T del S is negative, and del G negative, then spontaneous at all temperature, if such a scenario is there. But if del H is positive and del S is also positive, but minus T del S is negative and depends on the temperature, spontaneous at high temperature, but at low temperatures may not be spontaneous. And if you see del H is negative and del S is negative, so minus T del S, what will happen? It will be positive. So it is also depends on temperature, low temperature, because the low temperature means that T value is very important. So if it is positive and if it is low temperature, then the positive can be cancelled out the more negative del H. But it is high temperature, then it will not be. Then in this case, the spontaneity will not be there. And last case, that positive, negative, and positive, and for del G always positive, so it will not be spontaneous for any temperature. So reverse process may be the spontaneous process. Now, if you check this diagram, here you can see the boiling point where the gas is, the G curve of the gas is intersect with G curve of the liquid, and this is the G curve of the solid and G curves of the liquid. If it is intersect, this is a melting point. One is here, I am just talking about boiling point. Now there is a G versus temperature. Another is G versus pressure. If you check, the change in pressure influence the change in Gibbs energy for liquid and solid almost negligible, very less, very less. So that's why you can take G of function of T and pressure for a gas, but we can take G function of only capital T for a liquid and solid. Already we have discussed that. Now, for the purpose of few later few minutes discussion, we are taking a system that is liquid aluminium, and that solid enthalpy is Hs, solid entropy is Ss, and solid Gibbs energy is Gs, and liquid is Hl, and solid that is Sl. I just wrongly written Hl and Hg. This is Sl and Sg, and Gl and Gg. Okay. Now, if you see a scenario that Cp equals to, check a expression A, Bt, Ct square plus Dt cube, where A, B, C, and D are the correlation constant. Now we can know that Cp is a function of temperature. Okay. Now, if we integrate Cp by T dt, then we are going to get the entropy. If we integrate Cp dt, then we are going to get the enthalpy. And in the process, we can integrate and we can evaluate G of T. This is, we are talking about liquid and solid. Now, for Cp of solid, the constant, correlation constant A1, B1, C1, D1 in the expression 1, if you can see. And so, same way, the Cp of liquid A2, B2, and C2, one must remember or know that A must not equal to A2, B must not equal to B2, and C must not equal to C2, and as same way, the D's must not equal to D2. Because why is it so? Because atomic vibration in solid is not the same with the atomic vibration in the liquid. And that is the very important part. The way the liquid going to solidify and the solid does not going to melt it and the same way, means same rate. So this can be, there's a variation. Why it is a variation? The Cp of solid and Cp of liquid are not going to same. And that's why the enthalpy part also not going to same, the entropy also. So this is the very important concept. Now if you see, the unary system, the definition of equilibrium, we know that dg equals to 0. That means G of liquid equals to G of solid. Del G change in Gibbs energy is equals to 0. Now, if you check dgs equal to Vs dp minus S of dt, and dgl Vl dp minus Sl dt. Now, if you understand that liquid to solid transformation is occurring, then what is happened with the volume versus temperature term? There is a, if there is a, in case of aluminum, there is a sinkage. When liquid aluminum becomes solid aluminum, there is a volume sinkage. So change in volume, and that can be determined as a melting point of the melting point or point temperature of where it is going to solidify. And since it's a pure material, the temperature should be same single point temperature. For pure material, the boiling point, melting point are single temperature. Okay, and for the alloy, it can be a range of temperature based on the composition of that alloy. So here, if you check Vs minus Vl into dp equal to Ss minus Sl into dt. Now that part, if you reorganized properly, and already we know that del S equal to del H by Tm, melting point, and this is the entropy at the melting point or phase transformation temperature. Then again, from this expression, you can directly get that dt by dp equals to del V by del S, and del S equal to S of SS minus SL, means entropy of solid minus entropy of liquid, and same way entropy of the volume of solid and volume of liquids, a change in volume. So if you are talking about aluminium, so del V equal to which one is having higher volume? Liquid are having higher volume. So del V always negative, and same way you are also going to get the liquid are having higher entropy, so del also negative. So here you can check that from that liquid to solid, this is a latent heat. Del H change will be there, and that is actually latent heat. What is latent heat? The heat or enthalpy in the form of enthalpy or heat is required to transformation of a one state to another state, but it is not going to contribute towards the increment or decrement in the temperature. So temperature, from the temperature there is no change, but it actually helps to the transformation of the one state to another state. So if you check here, now there is a latent heat, and here suppose temperature and liquid to solid transformation is occurring, so there is a del T. So there is a time of solidification is important, that you have to have certain time to change all the liquid to solid, and also the latent heat is important. So for the time of solidification, you can check as a function of rate of heat extraction and heat of fusion. Del T you can write that del HF by del H by del T. So the solidification time is a function of rate of heat extraction, how quickly you can extract the heat, and that actually helps you to solidify the material as soon as possible, and also the amount of energy required to get to extract from that heat of fusion in the form of heat of fusion is very important. So here also you can see that dt by dp, this form of equation, that del V always negative and del S also negative for the aluminum. For the case of aluminum, it is totally different for the case of graphite and any other material. But for the aluminum we are discussing. So dt by dp also positive. Okay, so both are negative, then we are getting dt by dp is positive. Okay, and this is actually Clausius-Clapeyron equation or relationship. What is that? Dt by dp equal to del V by del S, or dp by dt equal to del S by del V. In the both form you can use. So what it means? The rate of change in melting point with respect to pressure can be determined using the above relationship. From there you can understand the rate of change in melting point with respect to defined pressure you can determine. And this is very significant concept if you want to do at least for secondary steel making operation, because pressure, the vacuum steel making technology or ladle metallurgy, the vacuum application of the vacuum is very important. The minimum vacuum level actually is very important part in order to refine the steel in the secondary steel making shop. And there this equation is very important, because there the concept of rate of change in melting point and all those things, how the dissolution of gases inside the liquid steel, you have to take care. Those things are very important. So Clausius-Clapeyron equations are very significant in such process understanding, at least in the case of secondary steel making process. And one note we should remember, it should be noted that the boiling temperature of all substances varies more rapidly with pressure than their melting temperature, since the large volume change during vaporization gives a small dp/dt. During the boiling point, the boiling of material, the change in volume is very high. So that boiling temperature of all the substances vary more rapidly, because the dt/dp, if you see, and change in volume is very high, then the effect of pressure will be very high with respect to pressure. And then if you check compared with the melting point, it's not going to get such kind of scenario, because the large volume change always associated with the vaporization process. Okay. Now we will see the variation of entropy with the temperature. For a reversible change, we know the entropy increment is ds equal to dq by t, and the variation of the entropy from T1 temperature to T2 temperature. Therefore, we can give like that this expression. But provided in between T1 or T2 there is no phase transformation, there is no transformation change in state of the material, then only we can tell such kind of things. For a process taking place at constant pressure and that does not involve any non-PV work, then we can write this expression dQB equal to dH equal to Cp dt, and you can write this kind of expression calculating entropy at particular temperature based on the entropy of a known entropy at a particular known temperature. If you know that entropy of at T1, you can try to calculate T2 temperature entropy based on your knowledge of Cp of that particular material. Okay. The entropy of a particular compound or element at a specific temperature can be determined through a measurements of heat capacity as a function of temperature. Already we understand from this expression. And adding temperature increments connected with the first order phase transformation. But if there is a first order phase transformation, then you have to consider this kind of term. During the change in phase transformation, what is the entropy and what is the transformation temperature, and all those things you have to understand and you have to consider. Now, certain questions are there that indicate whether the following processes are spontaneous or non-spontaneous. Liquid water freezing at a particular temperature below its freezing point, liquid water freezing at temperature above its freezing point, the combustion of gasoline, the ball thrown into the air, and raindrop falling to the ground, and iron rusting in a moisture process. You can check the spontaneity. Next slide, answer is there. But understanding the rationality to the answer is important. Suppose liquid water freezing at a temperature below its freezing point. Is it spontaneous or it is non-spontaneous? It must be spontaneous because at freezing point already from our discussion we understand that driving force is there, that is change in Gibbs free energy less than freezing point. If you check previous class video lecture, you can see that the driving force is there, so it is a spontaneous, so del G is negative. But liquid freezing at temperature above its maintenance, the driving force is not there. Here del G is positive, so it is a non-spontaneous process. The combustion of the gasoline must be spontaneous because it actually gives you del G negative. And ball thrown into the air. Ball thrown into the air means ball is going from lower energy states to higher energy state. So it is a non-spontaneous process. You are giving the energy from outside to increase the ball's potential energy. And spontaneous raindrop falling to the ground is a spontaneous process. It's actually decrease its potential energy. Iron rusting a moisture atmosphere, it's also a spontaneous process because here if you check for the reaction del G will be negative. Now questions. Many plastic material are organic polymer that contains carbon and hydrogen. The oxidation of this plastic in air to form carbon dioxide and water is a spontaneous process. However, plastic material tend to persist in the environment. Explain. This question actually help you to understand the difference between spontaneity and rapidity of a process. The answer, if you can check, although the oxidation of plastics is spontaneous, the rate of oxidation is very slow. Plastics are therefore kinetically stable, occurs appreciably even over relatively long periods of time. Although the process is thermodynamically spontaneous, but you can tell that the process is very slow, and that actually creates a problem, pollution and all kind of environmental issues. Another question. As we remember, that second law of thermodynamics says that del S is greater than 0 in the universe. So what should be different in a chemical reaction so that we could have the second case where del is less than 0? If you check from today's discussion, the second law states that entropy will increase or stay the same in a closed system. When you have a localized decrease in the entropy, you always have a increase in the entropy if you consider a larger system than the includes where the energy is coming from. So when you are talking about a small closed system, and if you consider the system boundary much larger, then your problem, that confusion, is going to be solved. So today class is over.